And we have some spectacular questions in the chat. Oh, yes, there are some good ones. So should we start with the more generic ones, or should we go right to the questions from our listeners? I think we should start with the ones from our listeners. Let's see. I like Jean. Let's see. The increase of wind speed detected by the altimeters, is it also detected from reanalyses? There is a weak trend, but it's much weaker than it should be, at least according to the other individual instrument records that we're looking at. So the reanalysis does not fully capture that. That's the difference between, but there is a trend. It's stronger in the tropics than it is in the Southern Ocean, like the wave power, et cetera. So we do have a bit of a mismatch. That's so I wanted to start with Andy and ask the really straight up question: what causes the ocean sink for carbon dioxide to change from year to year and decade to decade? What makes it go?
Well, I would we don't fully know. If we knew, I'd be writing a paper on it. But for my money, it's most likely it's because the ventilation rate of the ocean is changing. Well, you just shown, Joellen, that that the winds over the ocean are changing. So the really big thing that affects the uptake, the limiting factor on the uptake, we think, is ocean ventilation. So how the surface ocean gets into the deep, and what we're mostly focused on the quote anthropogenic uptake,
right.
And there's an interesting question about what the anthropogenic uptake really is. It's kind of easy to define in a model where it's just genuinely whatever the increase the increased stuff that
right.
the atmosphere.
It's not like the carbon molecules come it's not like the carbon molecules actually come tagged. They don't tell you I came from a fossil fuel versus I came from the deep ocean. There's no, they're not color-coded sheep.
Exactly.
We need to count them all, but
yeah. So what you're describing with the increase in upwelling in the Southern Ocean, for example, which might bring carbon into the atmosphere, that's not officially anthropogenic carbon, but if it's caused by climate change, then it doesn't matter. Yes. From the point of view of what it actually does.
People underestimate that acidification can happen from ingassing, but it can also happen from upwelling. Acidification happens in both ways, where we're lowering the pH of the near surface waters, and they happen from both mechanisms: a change in the circulation that brings up this more readily, this incredible reservoir of old carbon, that low pH water. It is. I'm always surprised at how much it's easy for the rest of the world to assume that they know what's going on in the carbon cycle because they're on Sarah's end of the spectrum, and we're going, hey, wait, we've got most of the carbon, right? So I just want to, there was what's driving the increase in wind speed? And I did say in my big talk, but kind of skimmed over that in my short talk. And I just wanted to say, it's primarily due to the fact that the lower atmosphere, our troposphere, is warming, but our upper atmosphere, the stratosphere laying right over it, is cooling, and it's cooling very quickly over the South Pole because of the ozone hole originally, but now also due to greenhouse gases. The change in the temperature is close to 7 degrees Kelvin, Celsius. And the warming in the troposphere is really only a couple of degrees, but that decrease in the stratosphere is like 4 degrees in the tropics. It's 2 to 3 degrees in the Arctic. So what they've done is the thermal wind, and I make my grad students do this on their orals. I'm terrible. They know I'm going to do it though. the thermal wind equation tells us that the bigger the temperature gradient, the bigger the wind, the bigger the flow. And so this is sort of just back of the envelope. You could do this. And Steve Sherwood out of the University of New South Wales has done an amazing paper actually looking at the increase in the winds associated with the correction you have to make to radiosondes trajectories because of the acceleration. So we have some pretty good evidence that this is, you know, when you add a cooling stratosphere, you increase the wind speeds. So everyone would like to think from paleo times that it's the equator to pole temperature gradient, but in a perturbed system, that is sort of climate sensitivity, the long-term 3,000-year thing. But what we're experiencing and our grandchildren will experience is that transient climate response. It's as the ocean equilibrates, we have a different pattern of warming. It doesn't look the same as the equilibrium will look. We have this different pattern. The Southern Ocean is going to be a huge player in this for a very long time, way past our great grandchildren. Sorry, go ahead, Andy.
So yeah, I mean, then of course ENSO and El Niños and La Niñas affect the rate of uptake of carbon dioxide as well. Absolutely. They may well be changing in the future. So there's these various climate modes, you know, the SAM, the Southern Annular Mode, which is, you know, changing, which I guess is the same thing as you're talking about. Basically, all of these climate modes will affect, you know, the uptake of CO2, and if they change, then the rate of uptake of CO2 is going to change. Yeah.
Increasing winds in the tropics may be explaining why we have these very different El Niños, where the normal slosh, that is that warm temperature anomaly, which we then see an increase in atmospheric CO2, both associated with burning on land from drought that is associated with the shifting of the rain with the water movement, also means that we have less solubility when we have a big El Nino. So you see an increase in the outgassing from, especially in the tropics, in the tropical Pacific. But so we know these things, we measure these things. I would love to see more carbon measurements in the tropics as well. In particular, because that outgassing is changing with the change in the winds. And we see some of the biggest trends in the tropics as well as the Southern Ocean. So these are really important. Now, I want to ask Bob, what sort of methodological approaches, and this is also, and then I'm going to ask Sarah. I have a couple for Sarah. So what sort of methodological approaches could be used to quantify organic carbon using BGC Argo or other platforms under variable conditions between the coast and the open ocean? You know, what do we have to do here to get at these questions on the organic side?
Okay, so on the organic side, typically, a lot of optical proxies are used to look at the organic carbon in the open ocean. So that can be the chlorophyll signatures, which is a measure of phytoplankton biomass, but also the backscattering signatures as well. So typically what we do is we relate the backscattering signatures to a particular organic carbon using the biogeochemical Argo floats to get sort of profiles of particular organic carbon and understand how that part of the organic carbon is responding to various things. It's a bit tricky when we get more closer to the coastal ocean, because various other components in the water can influence the backscattering signals. So we have sediments, we have potentially more non-organic matter that influences those backscattering signatures. What's quite nice with the biogeochemical Argo floats is we have these different optical signatures. So we have our chlorophyll, we have our backscattering, and we can start to tease apart perhaps the composition of the particles in the water, which has implications for various components of the ocean carbon cycle.
Awesome. So Sarah, what kind of, so I'm excited because when you show me that there are changes in what's coming off into the water around New Zealand, I get really excited because I'm like, oh, you guys are within our Southern Ocean state estimate where we already have the biogeochemistry. Has anybody looked to see if we are, now this is small and it might happen really close to the coast. Has anybody looked to see if there's a signature of New Zealand ocean? Is that happening in New Zealand?
No, I don't think anyone's, I have not looked at, and this is really on me, I'm the person who would know and do that. But I have not looked in depth at the,
wait till I get there. Wait till I get there. I'm coming for my Fulbright to New Zealand, hopefully this year. We had to postpone due to pandemic, but I want to help.
But you know, there could be, right? But there's like at present, there's not a lot of data from that part of New Zealand's coast.
We need a glider to go with our floats. And I need more deployed floats between you and Australia. We're still light there.
That area, yeah, between us and Australia, that area is really lightly.
I think it's because it's shallow, right? The Tasman Sea is relatively shallow and it worries all the float deployers, I think.
Okay.
Yeah. But yeah, this is what a frontier. Wouldn't it be great if we could see the puddle of organic carbon that New Zealand is creating?
I mean, and it'll be on the West Coast and the South Island, right? That's where the biggest puddle will be.
Ooh, right? I want to see. So what do you think we need to do in order to build a better carbon observing / accounting network? What do you need on the atmosphere side? We know we got our work cut out for us on the ocean side. What do you need on the atmosphere side? Where do you think the hot buttons are for countries like the US? Where could we dig in and make a difference?
Well, I mean, of course, the sampling density is hugely important, right? And so there are a few places
temporal,
where
not just spatial, but temporal too.
That's right. I mean, but usually those atmospheric observations, you have a site, right? And it's measuring all the time, right? So the temporal density kind of comes with it, right? Mm-hmm. But there are a few countries that have a really high sampling density in terms of the networks. New Zealand with our new deployments is getting there, UK. But places like the US could benefit a lot from a higher density of sampling.
We really haven't increased our funding for climate-related research. We've basically been robbing Peter to pay Paul in our national science budgets forever. We haven't seen big increases to address these sorts of things since the 70s. So I have high hopes that this will get the appropriate level of emphasis, since there are things we need to know that we could measure.
I mean, United States is a big island, right? Well, United States plus Canada is a big island. I mean, it should be possible to do a pretty good top-down estimate, surely, of the net budget of the United States, and presumably people have tried it. Should be able to do it pretty well, I would think, especially if we can lock down how much CO2 is going into the North Pacific and the North Atlantic on either side,
Yeah, I mean,
absolutely.
The NOAA group there has developed a lot of the modeling tools for that, and other groups as well. Like the work that Arlen Andrews has done with Carbon Tracker Lagrange is tremendous, right? It tends to look more at North America as opposed to, more nationalistically, right? As an area, right. They have a much harder problem with inflow than we have in New Zealand. So, we have to worry about what's coming off the ocean, but we're a long way from any other big land masses. And the variability and the pollution and all of the signals that are coming off of land masses are really big. So they do need some observations to help with that inflow condition, because you're seeing all kinds of stuff coming off of Europe and Asia and all over the place, as well as that ocean story. So that's a big complicating factor.
I've heard Colm Sweeney out from NOAA talking about instrumenting the nose cones of airplanes so that you get like a radius-on network worldwide sort of thing, where every up into the stratosphere and down as you land would get you a profile of atmospheric constituents like carbon dioxide, et cetera. What do you think about, I mean, imagine how many commercial planes we have that could be used to basically do like a radius-on network, except every day, all the time, every flight they make.
Every up and down. I mean, you'd see a lot of local pollution from airports though, right?
That's true.
The planes are mostly going down into towards the boundary layer at an airport. So it would depend a little bit on the pollution at the airport, which is.
But wouldn't you get a full profile above, you know, as you head up, wouldn't you get, you know, all the way to the stratosphere, basically?
Yeah, the upper layer. So as you move up through the atmosphere, you lose a bit of sensitivity to the surface. But then you also.
I just heard a lot of complaints. Yeah, I heard a lot of complaints about not having enough heavy lift aircraft to do the kind of measurements, wildfire season, that sort of thing. So I wondered, well, why not ships of opportunity the way that we oceanographers do it?
Yeah, that would be a really good program.
I think it would make a tremendous difference. I was talking with the director of ECMWF just recently, and she said that the single thing that makes the biggest difference to their normal weather forecast, you know, medium-term weather forecast, is the measurements that they get from commercial aircraft. As you say, most commercial aircraft now are producing, or large numbers of them are producing data which goes to the Met offices, and it makes a huge difference for the temperature and the physics. I would imagine it would make a big difference to the CO2 as well.
Well, I want to follow up with Bob, though. We've got people online who are really fascinated by pushing the ocean side on the DOC, on the dissolved organic carbon side. So in the atmosphere, there's more we could do. There's more that's already discussed, already being done for other tracers, just not the ones we're most interested in. But how about on the ocean, on the BGC Argo side? Whoops, did we lose? Where did I'm sorry, my question was here and somebody moved it. Stop moving it. Are there suitable optical proxies for dissolved organic carbon that could be measured with BGC Argo? DOC is a big reservoir. We're seeing how critical it is for looking at the puddle from our land masses. Is there something that could be done with that?
Well, potentially in the future. I mean, we've already seen new sensors being integrated into biogeochemical Argo floats and seeing new things. I mean, at present, what we can measure on biogeochemical Argo floats is the fluorescence from CDOM. And in coastal regions, there's often a fairly good correlation, or in some areas, a good reasonable correlation between DOC and CDOM concentration. So there's certainly a lot we can do, potentially looking at coastal runoff with biogeochemical Argo floats. I mean, one thing it's worth bearing in mind with these floats is there's a lot of really useful indirect information about the DOC cycles in the open ocean. So on the physics with the temperature, salinity, on the biology side and also on the chemistry side. So looking at, for instance, physical transport of DOC.
Right, yes.
On the surface in the deep ocean.
So okay, we're not the panel dealing with fisheries or nutrients, but I have a hard time imagining. So I'm looking at the Southern Ocean and the amount of nutrient trapping that's going on, i.e. that third thing that I had on the Southern Ocean, that vertical transport providing nutrients to the rest of the world ocean. We're looking at the carbon verification, but we could be looking at the nutrients, right? And the primary productivity changes associated with those nutrients. Are you going to be able to get, better estimates of primary productivity and the constituents that support it from BGC Argo floats? I mean, how's that? How much more are we going to be able to see as we roll these out worldwide?
Yeah, I mean, absolutely. I mean, there's a few things to bear in mind with these biogeochemical Argo floats. I mean, in my talk, I talked a lot about the synergies between what the satellite can see and what the biogeochemical Argo float can see. So light, for instance, we can see the surface light fields from space. We can also see the profiles from the float.
Right.
Same with chlorophyll, same with backscattering. But there's also additional information on these biogeochemical Argo floats, on the oxygen, on the nutrients, on the pH, which alone can provide additional information on constraining our estimates of primary production in the ocean. So, I mean, a global array of these biogeochemical Argo floats will be able to significantly reduce our uncertainties in that primary production.
Amazing. Amazing. Now, I'm really sorry because we're down to our last minute here. We filled it up. I was a little worried that maybe we would run out of things to say, but we're not even close. We still have this huge stack of questions. You'll be, if you come back this afternoon, you'll be bored because we're going to do this again, but we will get to more of the questions. It says where are we with uncertainty of CO2 measurements? Let's see, why is it that the models and observations, Andy, are different around the year 2000? There are so many interesting things we could talk about, but thank you, Sarah. Thank you, Andy. Thank you, Bob, for joining us. And thank you to our sponsors, to the National Science Foundation and NOAA and NASA and the rest of our international supporters here. We are so grateful that people are starting to pay attention and help us grow here. Isn't it exciting? We're pioneering. Woohoo! Andrea, was there anything else you wanted to end with here?
Nope, I think that's everything. Just thanks to everybody for joining.
Yep.
Join us again for our next session this evening.
Yep. We'll do this again this evening if you want to join us. Thank you so much and have a great rest of your day or evening. Bye-bye.
See you later. Bye.
Bye.